This is Mr. Oberbeck, and welcome to another video lesson. In this lesson, we're going to be discussing different definitions that pertain to circles. We're also going to look at a relationship with tangent lines and circles as well. Let's get started. Our first term we're going to discuss is radius. And for definition, a radius is a segment on a circle whose endpoints are the center of the circle and a point that is on the circle. Translating our definition to our diagram, we're going to go ahead and label the center of our circle. We'll call that O. And then we have a point on our circle, which we can call point A. And by connecting our center to that point, we have now drawn the radius. Our next term is diameter. For our definition, we have a segment whose endpoints are points on the circle and that pass through the center of the circle. Again, looking back at our diagram, if I want to translate this to our picture, we have center of our circle, C, and then have 2 points. We have point A and point B. And when we connect them, our diameter is going to go from point A to point B and pass through the center of our circle, making a straight line and representing our diameter. As a side note, since our diameter goes through the center of the circle, it does cut our circle into 2 equal halves. Moving on to a chord, our definition states we have a segment whose endpoints are both on the circle. Translating our definition to our diagram now, again, we're going to have 2 points, point A and B, and we're going to connect those 2 points. I could draw my chord a little differently. So let's say I have 2 separate points. I have point C and I have point D. I could connect those 2 points. Again, I have 2 points on my circle and I connected them with a segment, giving me another chord. With our secant, we have something that is similar to a chord, but now instead of a segment, we have a line. And our line is going to intersect a circle twice. So again, we're going to have 2 points. We have point A and point B. And I'm going to connect my 2 points with a line this time instead of a segment. And I'll show that I have a line by putting my arrows on the outside to show that it keeps going. I could have drawn my line a little differently. So let's say I have point C and have point D. I could have connected those 2 points, again with a line, and I would still have a secant because it's intersecting my circle twice. For our tangent, we again have a line, but this line is going to intersect a circle exactly once. And so what that means is we're going to be touching our circle, but we don't exactly get to cross through. And we touch at a point that we call the point of tangency. So here I'm going to draw point A, and point A is going to be my point of tangency because that's the only location that my line is going to touch my circle. So when I draw my line, I cross through point A, and I don't actually cross into the circle, I just touch it on the outside. Continuing with the idea of tangents, now we have tangent circles. And similarly to our tangent intersecting our circle at one point, tangent circles are going to intersect at one point. There are 2 different ways that we can draw tangent circles. Our first option is we draw our second circle on the outside of the original circle. So again, I have my point of tangency, which I'll call point A. And when I draw my second circle, I'm going to draw it again on the outside, touching the first circle at only point A. The second option is now I'm going to draw my circle on the inside of my original circle. We'll call this point B. And when I draw my second circle, again, it's going to be on the inside, and it touches just at point B. So again, our circles touch at only one point, which is again called the point of tangency. Concentric circles are 2 circles with the same center. As an example, with my 2 circles here, I would take my second circle and I would make sure that the center for both circles are now going to be the same center. So I'd have my center point here, point C, and again, both circles have the exact same center, making them concentric circles. For our last term here, we have a common tangent. And for our definition, we have a tangent line that intersects two circles at one point. There are two types of common tangent lines that we can draw. There are internal and external tangent lines. For your internal tangent lines, they're going to be going inside of our two circles. So we would have something that kind of crosses in the middle. And again, would touch at only 2 points, point A and point B. We could draw it from the top going down as well. And we'd have point C and point D. For our external tangent lines, these are drawn on the outside of our circles. Again, touching at just 1 point on each circle. We can call this point A for our bottom diagram, and this be point B. We could also draw one on the lower portion. Again, touching at just 1 point on each circle, giving us our external tangent lines. Now that we've discussed some of our terms, we're going to further explore the relationship between tangent lines and circles and use them to help us solve for some different lengths and measurements. The first relationship we're going to explore is the angle formed between the line tangent to a circle and the radius of a circle. In our diagram, we have line LP, which is a tangent line to our circle, and we know it's a tangent line because it's only touching at point P. If I were to draw the radius of my circle, going from center O to point P where my tangent line is drawn, what would the relationship of the angle that is formed be? So what kind of angle are we creating by drawing our tangent line and connecting it to our radius? Go ahead and take a moment to think on that. Looking at the diagram here, you might be able to guess what the relationship is, but we're going to go ahead and write a definitive conclusion here. So for our conclusion, we have a line that is tangent to a circle is perpendicular to the radius of the circle. Given that we have perpendicular lines, we can then make the claim that where your radius and your tangent line meet is a 90-degree angle. For our second scenario, what do you think the relationship is between two tangent lines that intersect outside of our circle? So we have line 1 and we have line 2. They're both tangent lines because they touch our circle at only 1 point and they intersect outside of our circle. So the question now is, what is the relationship between line 1 and line 2? Go ahead and take a minute to think about that. Using our previous relationship, we know that if a tangent line has a point of tangency with our radius, then we connect with a 90-degree angle. So we have two 90-degree angles. I also know that the radius must be congruent to another radius within a circle. If I were to connect the center of my circle to my point that is outside of the circle, I've created a second congruent side. And now, if I were to walk through a proof using the Pythagorean theorem, I could then show that the tangents, or the third side for each one of my triangles, must be congruent. So for our conclusion, when two tangents on the same circle meet at a common point outside of the circle, the segments formed from the circle to the point on the outside are congruent. We're now going to go ahead and work through some problems applying this relationship, helping us solve for some missing variables and also solve for some missing segments. For our first example here, we're given some information. We know that JH is a tangent line to circle L at H, meaning that H is our point of tangency. We also know that JK is a tangent to circle L at K. So we have two tangent lines, again, line JH and line JK, and we can see that they meet at point J. So these are two tangent lines that meet outside of our circle. Using our previous slide, we can use a relationship that we know those two tangent lines have to be equal. So I'm going to start off with a sentence here that KJ must be congruent to JH. Knowing that they're congruent, I can then go ahead and plug in an expression for each tangent line. I know that KJ is actually 61, and I know that JH is 7x minus 23, so I can plug those in. And I can go ahead and go through the process of solving for my variable to identify what x is, since that's what my question, finding the value of x. I would add 23 to both sides, and we get 84 is equal to 7x. And then we can divide both sides by 7, and we finish getting that x is equal to 12 as our final answer. Applying that same property in our second example here, we see that we have SR and RT that are both tangents to circle Q. We want to find the length of SR. So knowing that SR and RT are both tangent lines and they intersect at a point outside of our circle at R, I know that they have to be congruent. So I know that SR has to be equal to RT. By plugging in what SR and what TR are represented from our diagram, I get my following equation of n plus 3 equals 2n minus 1. My goal now is to go ahead and get n by itself, so I'm going to start by adding 1 to both sides. And we have n plus 4 is equal to 2n. If I then subtract n on both sides, then we get 4 is equal to n. Now I know that n is 4, but my question really is to find SR. So I want to make sure I'm using my information to help me find that. Looking at my diagram, I see that SR is equal to n plus 3. So I can go ahead and plug in my n value. And instead of n plus 3, we now have 4 plus 3, which tells me that SR has to equal 7. If I had a follow-up question asking me about RT, going back to the idea that these are both tangent lines that intersect outside of a circle, I could say that RT is also going to be the same, which would be 7. All right, now it is your turn. Go ahead and try and solve for x using the diagram given to you. Go ahead and hit pause and write down your answer. Using the previous two examples, we can see that again we have two tangent lines that are going to intersect outside of our circle. So I can say that they must be congruent, which means for my equation, I would just say that 13 is equal to x. And since there's no other algebra to be done to solve for x, I have my final answer, x equals 13. For this diagram, we see that JK and JL are both tangent lines to the circle, and the question is to find JK. So go ahead and hit pause, try and find x, and use it to help you find JK. For this example, noticing that JK and JL are tangents that intersect outside of our circle, we can say they're congruent to each other. So for my equation, we have 4x minus 1 is equal to 2x plus 9. We're then going to go ahead and get x by itself, so I'm going to start by subtracting 2x on both sides. And we get 2x minus 1 is equal to 9. I'm then going to add 1 to both sides, and we have 2x is equal to 10. And finally, dividing by 2, we get x is equal to 5. Our question is to go ahead and find jk, so I'm going to take that x and plug it into my expression for jk, which was 4x minus 1. So now instead of 4x minus 1, we have 4 times 5 minus 1, which is going to be 19, which tells me that jk is going to equal 19. And again, since our tangents are congruent, that would also mean that JL also equals 19. In this example, we again have two tangent lines that intersect outside of our circle. We have AB represented by x squared plus 5 and AD represented by 3x squared minus 4. Since these are both tangent lines that intersect outside of our circle, we know they have to be congruent. So our equation then to help us solve for x is going to be x squared plus 5 equals 3x squared minus 4. Just like our previous examples, we're going to get x by itself, so we're going to go ahead and add 4 to both sides. And we get x squared plus 9 is equal to 3x squared. Then you're going to go ahead and subtract x squared on both sides. And we get 9 is equal to 2x squared. To finish solving for x squared, we're going to divide by 2. And we get 4.5 is equal to x squared. And now for my last step, we're going to go ahead and take the square root of both sides. And we get that x is approximately plus or minus 2.12. And since we were asked to solve for x, that is our final step, and we are done. X is equal to approximately plus or minus 2.12. Your turn to give this a try. For our final example, we have AB and AD are both tangent to a circle. AB is equal to 4x squared minus 2x plus 3, and AD is equal to 5x squared minus 2x minus 13. So go ahead and hit pause now and try and solve for x using the information given to you. Using the information given to us, we know that AB is equal to 4x squared minus 2x plus 3, and we know that AD is equal to 5x squared minus 2x minus 13. Again, since these are tangent lines that intersect outside of a circle, we know that they have to be congruent, so I'm going to start by setting my expressions equal to each other. So we have 4x squared minus 2x plus 3 is equal to 5x squared minus 2x minus 13. We need to go ahead and try and get x by itself, so I'm going to start to combine like terms. I'm going to add 2x to both sides. And I'll notice that it will cancel out on both sides. And then I'm going to add 13. and we have 4x squared plus 16 is equal to 5x squared. I'm going to subtract 4x squared on both sides, and we get 16 is equal to x squared. Then we're going to take the square root, and just like with the last example, don't forget to add in plus or minus. We're going to be getting plus or minus 4 is equal to x. Checking our question, we were asked to just solve for x, and since we've done that, we are done. That completes the video notes for this lesson. Go ahead and get started on the assignment, and good luck.